Alright, so something interesting that's come up in our discussion of projectile motion. We've spent a lot of time looking at two of the three fundamental one-dimensional equations of motion. And I'm going to try something new here and represent these things with a box. So let me just draw this, or let me just do one of these to show you what I mean. So box equals box naught plus initial velocity in the box direction times t plus 1/2 acceleration in the box direction times t squared. And this is for constant acceleration. And then the other one, and the idea is you can replace box with x or y or z and have a true equation in any of these. And then the other one is v in box is equal to initial velocity in box plus a in box times t. Okay, so far this is all working out pretty well. So we've dealt a lot with this equation and this equation, but we haven't talked a whole lot about the third one, which is v box squared equals v naught in box squared plus 2 times a in box times delta box. And now I've got a triangle and a square in the parentheses together, so this looks extremely weird, but just imagine the box is an x, a y, or a z, so acceleration in x times the change in x, for example. So this is kind of interesting because there's actually something interesting there's something neat you can do with this third equation here that we haven't spent much time on, but I'm going to derive this for you and then show you what it means. So we can let's take it in x. So I'm just going to say the box. We turn it. Well, that's almost off the screen. There's our box. Becomes x, and then we get vx squared equals initial velocity in x squared plus 2 times the acceleration in the x direction times the displacement in x. That's all fine and good. V sub y squared equals initial velocity in y squared plus 2 times the acceleration in y times delta y. Okay, and just for the hell of it, let's go ahead and do it with z. Vz squared equals v naught in z squared plus 2 times acceleration in z times delta z. And if we add all these equations up, let me fix that one there, that's a little better. If we add all these equations up, what we get is vx squared plus vy squared plus vz squared equals v naught in x squared plus v naught in y squared plus v naught in z squared plus 2, and I'm going to collect all these terms, a sub x delta x plus a sub y delta y plus a sub z delta z. Well, let's write that down there. A sub z delta z. You get the idea. Okay. So, oh, son of a gun, why didn't that come out? A sub x, there we go, that's a little better. Okay, so what we can see if we look at this is that we're taking here the x component of the velocity, squaring it, adding it to the square of the y component of the velocity, and adding it to the square of the z component of the velocity. Now, if you remember the Pythagorean theorem, what we're really doing here is just finding the square of the magnitude of the velocity, which, as you'll recall, is just the speed. Okay, v. So v squared, and then we're doing the same thing over here, squaring 3 components of the initial velocity, adding them up. So that becomes the initial velocity squared, and then plus 2, and then this little creature over here, this little string of things over here, a sub x delta x plus a sub y delta y plus a sub z delta z. Okay, so what I submit to you is that this looks, oops, let me try to get that. That looks pretty good. Okay, what I am suggesting here is we have this relationship for speed, from initial speed, that just depends on these, adding up these three quantities. And if you look at this, we've got the x component of acceleration, y component of acceleration, and z component of acceleration, and we're multiplying by x component of displacement, y component of displacement, and z component of displacement, and adding them all up. What is that? That is the dot product, if you recall, from our work on vectors. So v squared now equals v naught squared plus 2 times acceleration dot displacement. Remember, we use r for position, so delta r is displacement. Okay. A is acceleration. And this is the number 2, of course. Let me see if I can make sure that looks a little more like a 2 and not like a z. This is v. So, wow, that looks ugly. Jeez. All right, let me see if I can fix that a little. Okay. And let me get my pen back. And there we go. So there's a v. That's a little better. All right, so this is speed. Yeah. Speed is there. And initial speed is right here. So we've got this equation relating current speed to initial speed, and then to acceleration, constant acceleration. So let me write down here the acceleration is constant, to displacement. And what's interesting is that this equation, these two equations, or these two values, we don't care what direction it's going in. We just care about the speed. So this is something that can be kind of useful sometimes when you just need to get a speed relationship. And we're especially going to see this much more often later on when we get into energy and work, where we'll find that this term relates to current kinetic energy, this term relates to initial kinetic energy, and this term relates to the work done during the intervening time. So let me just write this down here one last time to make sure it's sort of clear for everyone. V squared equals v naught squared plus 2a vector dot product delta r vector. And that is something we will be using later on.